Hi, everyone. Today we are going through some problems on proofs, the pigeonhole principle, and contradiction. So let's get to the first problem. Okay, so we'll go back to the first one in the slides a little bit later, but we'll start with this one. It says use the pigeonhole principle to prove the following. Given any 5 integers, there will be 2 that have a sum or difference divisible by 7. So we'll give you 5 minutes to think about this, and then we'll start to discuss it. All right. So I just wanted to give you guys a little more time on this one because it requires, some thinking, just as all the problems do, but this one requires a lot of thinking as well. So let's just start with some notation to get going. We have 5 integers. So let's just label them. We'll call them A1, A2, A3, A4, and A5. And they're all integers, so they're all in Z. And we want to show that there must be 2 that have a sum or difference divisible by 7. So does anybody who thought about this problem want to start us off just by telling us a little bit about their strategy? Before I just, start doing it. If anyone would like to say anything about their strategy or thoughts they had about the problem, go ahead.
Will there be 0, 1, 2, 3, 4, 5, 6?
Yeah, so when I think I know what you're saying here, which is that when we divide each of these numbers by, like if we divide A1 by 7, then its remainder is either 0, 1, 2, 3, 4, 5, or 6. So that's a really important observation for this problem. We're interested in finding a pair of numbers that when we take their sum or difference, they're divisible by 7. So we need to start thinking about what happens when we take our numbers, our integers, and divide them by 7. And the first key observation is that the remainder of one of these numbers, when we divide it by 7, is either 0, this is a 0, 1, 2, 3, 4, 5, or 6. So let's keep going with that idea. Let's make 4 different boxes. We're gonna divide up the possibilities here. So it could be that when I take A1 or A2 or any of these numbers, that its remainder is 0. So if we did have 2 numbers and their remainders were both 0 when we divided them by 7, that would mean they were both multiples of 7. But we'll get to that in a second. Let's keep on dividing up the cases here. So it could also be that when I take an integer, that its remainder is 1, or its remainder is 6. Okay. It could also be that so this is just one way to divide up the cases about what the remainder will be when we take one of these integers and divide it by 7. So another possibility is that the remainder is 2 or 5. And then one last possibility that we haven't covered yet is that the remainder is 3 or 4. Okay. So when we take an integer and we divide it by 7, it has a remainder, and that remainder falls into one of these 4 buckets. Okay, so we know that. So we want to show that there are 2 integers in here such that their sum or difference will be divisible by 7. So we have 5 integers. We have 4 buckets. By the pigeonhole principle, two integers fall in one bucket. So two integers fall in one bucket. It might be A3 and A4 that fall in the same bucket. It might be A1 and A2 that fall in the same bucket. For notation, we could just say, let's just try to be exact. We'll say that the two integers that fall in the same bucket are AI and AJ. Okay, so here AI and AJ fall in the same bucket, and I and J are in 1 through 5. So, it could be that I is 1 and J is 2, but it could also be that I is 3 and J is 5. All we know is that AI and AJ fall by the pigeonhole principle. They fall in the same bucket. All in the same bucket. And the reason is because we have 4 buckets. We have 5 integers. Every integer must fall into one bucket. And so by the pigeonhole principle, we must have 2 integers that fall into the same bucket. Their indices are I and J. So we now know that AI and AJ fall in the same bucket. So no one told us which bucket this is, so we have to go through some different possibilities. Let's say that possibility 1 is that AI and AJ are in the first bucket. That's this bucket. That means that their remainder when divided by 7 is 0. In particular, so this is case 1. This is case 1. So AI is a multiple of 7 because it falls in this bucket. Its remainder when divided by 7 is 0. It falls in this bucket. So for some integer k, AI is 7k. And the same goes for AJ because AJ falls in this bucket. So AJ is 7m for some integer m. So if we add or subtract AI, so if we add AI and AJ, we're left with 7 times m plus k. M plus k is an integer, and therefore AI plus AJ is divisible by 7, and we're done. So does that case make sense? Are there any questions up to this point? All right, it's going to get slightly more complicated, but not too much more complicated as we finish this. So if you have any questions about the previous part, speak up whenever and we can resolve it. So the second case is that AI and AJ fall in this bucket. Okay, so there are 2 possibilities that we really have to deal with. So we're in this bucket. So AI and AJ are in this bucket. It could be that their remainder when divided by 7 for both of them is 1. So let's deal with that. Let's see what would happen if that was the case. So let's just say, so I'm just going to say, so possibility A is that their AI and AJ are both have remainder 1. Both have remainder 1. All right. So what does that mean? Well, then AI by the division theorem is 7k plus 1 for some integer k. And AJ is 7m plus 1 for some integer m. That's what it means for them both to have remainder 1. So that means that AI minus AJ, that's equal to, well, 7k plus 1 minus 7m plus 1. The 7 cancels. The 1 cancels. And we're left with k minus m. And k and m are both integers. So k minus m is an integer by closure of the integers under addition and subtraction. And so the difference AI minus AJ is divisible by 7. Okay, so we just handled one possibility in this bucket. So we had, again, just to reset where we're at right now, we had 5 integers. We know that when we take any one of these integers and we divide it by 7, that it has a remainder, and that remainder is between 0, it's either 0, 1, 2, 3, 4, 5, or 6. And we divided up these remainders into 4 different cases: that the remainder is 0, that the remainder is 1 or 6, 2 or 5, or 3 or 4. Those are our 4 cases. We have 5 integers, and we have 4 buckets, and each integer must fall into one bucket. So by the pigeonhole principle, we have 2 integers that fall into the same bucket. We just, we don't know which bucket that is, so we have to go through, enumerate all of the different possibilities. And so the first possibility is that the 2 integers fall in this bucket. And we saw when that was the case, then AI plus AJ was divisible by 7. Now we're dealing with this second case. And so here, there are actually 3 distinct possibilities, and we've just dealt with the first one. So the first one is that AI and AJ both have remainder 1. And when that was the case, then we took the difference between AI and AJ, and that was divisible by 7. So similarly, the second case, the second case is, so case B for C2. So this is also for case C2. The second case B is that AI and AJ are both divisible, they both have remainder 6. Both have remainder 6. Remainder 6. Okay. And this case is handled almost identically to case A. The 6 will cancel when we take the difference between AI and AJ, and therefore the difference will be divisible by 7. So then we only have one more case within C2 to consider, and that's when one of these 2 integers has remainder 1, and the other one has remainder 6. So in that case, so this is case C, then AI is, let's say that's the one that has remainder 1. So that's 7k plus 1. And then we have AJ, and that's 7k plus 6. 7m plus 6. 7m plus 6. Okay. So that's extremely difficult to read. Sorry. Let's see here. 7m plus 6. Okay. So then when we add AI and AJ, well, the 6 and the 1 add to 7, and we have then 7 times m plus k plus 7. And so that's 7 times m plus k plus 1. And so that means that AI plus AJ is divisible by 7. So we've now handled all of the cases in box 2, in this box. So this was box 2. We suppose that AI and AJ were both in this box. There were 3 different possibilities. The first possibility was that both AI and AJ had remainder 1. I see the question in the chat. I'll look at that in a moment. The second one was that AI and AJ both had remainder 6. We handled that. And the third case was that one of the integers had remainder 1, the other one had remainder 6. And in that case, we we were fine too. So there's a question in the chat. Is there a faster way to prove this? Well, you don't have to go through it. I mean, is there a faster way to prove it? Well, okay, so I guess there's one place where this could be made more efficient. When you get into case C2, if you're in this box, if you're in this box, I understand what you're saying, Ethan. If you're in this box, or this box, the key idea is that when you add these remainders, they always add to 7. So instead of enumerating the cases like this, I wanted to enumerate the cases so deliberately so everyone understood what was happening. But if you're in a hurry on an exam, then what you're going to want to say is that for these 3 boxes, you can basically handle them together by replacing you replace the 1 and the 6 with an R1 and an R2. And you say that whenever we're in one of these 3 boxes, R1 plus R2 is equal to 7. And so that's how you would speed up the proof. It's yeah. Yeah. Are there any additional questions about this problem?
I have a question.
Mhm.
For case 2C, what if we have like 6 minus 1 instead of adding them together?
So we only have to show that there exist 2 integers such that either their sum or their difference is divisible by 6.
All right. Okay. Yes. Thank you.
Yep. All right. So if there's no other questions, then we'll move on to another problem. So let's see. Okay. I'm going to erase what's on the screen from that problem. So I guess if you do have other questions about it, then there will be chances to ask about it in office hours. For example, James has office hours today at 4. I have office hours on today. James has office hours today at 2. I have office hours on Monday at 8 a.m. So if you're still struggling with this problem, make sure that you go to office hours. James, did you have something you wanted to add?
Oh no, I was just clarifying. Yeah, the times from 2 to 4.
Okay, thank you. All right, so let's move on to this problem. Okay, so prove the following by using the contrapositive for all real numbers x and y. If x squared plus y squared is not equal to 0, then x is not 0 or y is not 0. So I'll give you a minute and then we'll do this one. All right. So does anybody want to share what their strategy was for this one?
Well, it'd be 0. You put it 0.
Yes, yes. So I think I see what you're saying. So yes, eventually we're going to conclude that 0 equals 0, and that's going to finish this proof. So the first thing is we'll write down what the contrapositive is. So just to simplify things, let's let this statement be P, and this statement be Q. So the contrapositive is going to be that not Q implies not P, because the statement here is that P implies Q. So we write down what not Q is. So not Q, that's that this statement is false. So now we're going to use De Morgan's rule. So this becomes x is equal to 0 and y is equal to 0. So not Q is the statement x equals 0 and y equals 0. And then not P, so we not P is the statement there exists real numbers x and y. Oh, hold on a second. Wait. Sorry. This is not P. Sorry, I should not have said that. Let me erase. So P is the state. So we're fixing two real numbers, x and y, and P is the statement that x squared plus y squared is not equal to 0. So sorry about that. So this is P. That's P. So not P is that x squared plus y squared is equal to 0. So not P is that x squared plus y squared is equal to 0. Okay, so we want to show that if x and y are both 0, that's not Q. Then that should imply not P, which is that x squared plus y squared equals 0. And so as Yu was saying, we just plug in x and y into this expression, and we end up with 0 squared plus 0 squared is equal to 0. And so we've done it. And another thing to keep in mind is that this makes sense because the implication is logically equivalent to the contrapositive. So that's why we could prove the contrapositive, and that proves the statement. So. Are there any thoughts or concerns about this one? All right. Okay, here's another one. Use induction to prove this statement. So I'll give you a 3 minutes to get it started, and then we'll do it. I am now unmuted. If we are trying to prove a statement by induction, then we want to start with a predicate. And that predicate we will prove is true for every integer n greater than or equal to 1. So let's start by writing out what the predicate is. The predicate is what we want to prove for every integer n greater than or equal to 1. Would anybody, does anybody know what the predicate is here? You could type it in the chat or shout it out.
For all j less than n, that some quantity is 2 to the j plus 1 minus j minus 2.
Yes, yes. So, and I'm just going to replace j with n here, but you can use whatever letter you want. So just as Alec was saying, we want to show for every integer n. So the predicate here is, so this is our statement. This is our statement P of n, and that's that the sum from I equal 1 to n of 2 to the I minus 1 is equal to 2 to the n plus 1 minus n minus 2. So that's our statement. That's what we want to show is true for every integer n greater than or equal to 1. That's our predicate. So all right, let's do it for the base case. So it's induction. So we start out with the base case. So the base case is when n is equal to 1. So let's do P of 1. Let's prove that P of 1 is a true statement. Just gonna put some colons there. All right, so the left-hand side is, so n is equal to 1 here, so there's only one term in this sum, and that's 2 to the first minus 1. So this is the left-hand side. And the right-hand side is 2 to the first plus 1 minus 1 minus 2. This is the right-hand side. And so this is 4 minus 1 minus 2, which is 1. And this is 2 minus 1, which is 1. And so we have that the left-hand side and the right-hand side are the same. So P of 1 is proven. So this is equal. And we have P of 1. Okay. So now we need to do the inductive step. So this is our standard algorithm for doing a proof by induction. So let's suppose that P of n is true. P of n is true for some n, n greater than or equal to 1, which is an integer. So just because it takes a while to write that, I'm just going to say n greater than or equal to 1. N is an integer here. And we want to show that Pn plus 1 is true. Okay. So this is our inductive, we're proving the inductive step. So we've assumed that for some integer n, P of n is true, and we wish to show that P of n plus 1 is true. So the left-hand side is a sum, and we, so this is what we want to show, so let's just try to do it. It's a little bit difficult to write out exactly what P of n plus 1 is, but we'll see as we go. This is kind of what you can do here. So we want to make a statement about the sum I equal 1 to n plus 1 of 2 to the I minus 1 Okay, we know that P of n is true, so let's use it. So we'll break up this sum into two pieces, the first n terms and the last term. So remember, P of n tells us about the sum of the first n terms. So that's why we're breaking it up. We're trying to use P of n. So that's an n, 2i minus 1, and then we add this last term. So the last term is the n plus 1th term. So that's 2 to the n plus 1 minus 1. All right. Now we're going to use our inductive hypothesis, P of n. We know that P of n is true. So P of n tells us what this sum is. It's 2 to the n plus 1 minus n minus 2. So let's write that out. N plus 1 minus n minus 2. All right, and then we also have the second piece, and that's 2 to the n plus 1 minus 1. All right, so at this point, if we don't know where we're trying to go, then we'll just get kind of lost. So we really have to think about what do we need to show here. Otherwise, if I just hammer through the steps and then say, oh, we got what we wanted at the end, and then tell you what we were looking for, it's like magical, and that's just not useful. So what you need to be thinking at this point is, where do I need to go? That's going to tell us how we need to simplify this expression. So P of n plus 1 is that I'm going to change this for now. So P of n plus 1 is this statement. It's that this sum is equal to 2 to the n plus 1 plus 1 minus n plus 1. Oh my goodness. Minus n plus 1 minus 2. Actually, let me make that more readable. Okay, so this is minus n plus 1 minus 2. Okay, so instead of writing P of n here, I've written out P of n plus 1. We're not changing anything about the problem. We just need to know what P of n plus 1 is. Otherwise, how will we know how to prove it? We won't. So we need to write it out. So it's 2 to the n plus 1 minus n plus 1 minus 2. So what we have here is the left-hand side of our P of n plus 1. We need to show that it's equal to the right-hand side. So that indicates how we're going to simplify this expression. So we're going to combine our 2 to the n plus 1s. There are two of them, so let's just write that out. All right. And then we have a minus 2 and a minus 1, and we have a minus n. Let's just put it all together for a moment. We have a minus n minus 3. Okay. So, well, we wanted to get a 2 to the n plus 1 plus 1. And we have 2 times 2 to the n plus 1. So the base is 2 here. This is like 2 to the first. The powers add. This is a property of exponents. With a common base, the powers add. So this is 2 to the n plus 2. And we'll just write that as 2 to the n plus 1 because we wanted 2 to the n plus 1 plus 1. And then we have a minus n minus 3. So we can rewrite this as well. We wanted this minus quantity n plus 1 minus 2, and that happens to be minus n minus 3. So the reason here is that when we distribute this negative sign, that's a minus n. When we distribute it, you get a minus 1, and then you have minus 2, and that's minus 3. So we have just shown that P of n plus 1 is true. So we assumed P of n, and we proved P of n plus 1. We also showed that P of 1 was true, and so by induction we have P of n for every n greater than or equal to 1. And so we're done. Are there any questions about anything that we did in this problem?
I have a question. I just want to ask, sometimes I feel like we use n minus 1, but how do we know when to use -1, when to use n plus 1?
This is a choice that you make. I'll explain that on a different on another page. But is there anything on this piece of paper that you want to, if you want to write it down, now is the time to do that, because I'm going to go to another page and it's going to disappear.
Oh, also, when we do the base case, do we generally just use the smallest number of this? In this case, is n greater or equal to 1, so we use 1. But if it's n greater or equal to 0, do we use 0 then?
Yes, yes. Yeah, to answer your question, yes. Every problem is going to be a little bit different. Sometimes your when you read the problem, it'll usually kind of make clear what the starting points need to be. So, all right. So I'm going to go to another page here to explain that other point, which I think Alec asked about this last week. So let me just explain this. So, induction is like a ladder, and so we have a base case, and what we want to be able to do, what we want to prove, is that we can always so the base case is the first rung on the ladder, and so by proving the base case, we get to that rung of the ladder. So we are now we have proven P of 1. What we want to show is that we can climb to any rung of the ladder. So the next rung of the ladder is P of 2, P of 3, and so on, P of 4. So, and P of 5. Okay, so what we want to show, out of this analogy is that P of n is true, P of n true for all n greater than or equal to 1. That is what we want to show, and this analogy is that, well, if we're able to climb to the third rung of the ladder, then we have shown that P of 3 is true. So what we did on the previous page was we showed this base case, P of 1, and then we argued that P of n implies P of n plus 1 for all n greater than or equal to 1. And what that means is that, in particular, since we proved P of 1, we know that P of 1 implies P of 2. Because we proved for a general n greater than or equal to 1 that P of n implies P of n plus 1. So in our ladder analogy, from the base case, we were here, and using the inductive step, we were able to climb one rung of the ladder. And so we have now proven P of 2. So if you want to prove P of 3 now, then we use the inductive hypothesis again. We know that for every n greater than or equal to 1, P of n implies P of n plus 1. In particular, P of 2 implies P of 3. So we know that P of 3 is true. Okay, so we have been able to climb another rung of the ladder. And so you can do this for any integer greater than or equal to 1. And so we now know that P of n is true for every integer greater than or equal to 1. In the analogy, we can climb to any rung that we want on the ladder. And now your question is, well, why not do this? Why not show that P of n minus 1 implies P of n for any n greater than or equal to 2? Is that the question?
So they said in chat, yes, that answered.
Oh, okay, thank you. So, well, we already proved the base case. So you're saying let's replace this with this. So that's completely valid. Instead of doing this, we could have done this, and we proved P of 1. So if we proved P of n minus 1 implies P of n for every n greater than or equal to 2, then we proved in particular that P of 2 minus 1 implies P of 2. Because we proved that P of n minus 1 implies P of n for every n greater than or equal to 2. In particular, we proved it for n equal to 2. So this is a 2, and that's a 1. So we now know that P of 2 minus 1 implies P of 2. So P of 1 implies P of 2. And we already know that P of 1 is true because it was our base case. And therefore, P of 2 is true. So now, using this statement, which we know is true, we can then show that P of 3 is true. We plug in n equal to 3, and we have that P of 3 minus, P of 3 minus 1 implies P of 3. And we know that P of 2 is true. So we've just shown that P of 3 is true. So, both strategies are valid. And when I'm in class and okay, all right. Okay, so there's only there's 2 minutes left. Let's look at another question. Let's just look at it. Oh yeah, all right. So here's the question, and I'm just going to explain the strategy because we don't have that much time left. Prove that the square of an integer not divisible by 5 leaves a remainder of 1 or 4 when divided by 5. All right, so you get one of these divisibility problems. So division theorem. That's what was on our mind before, and so it can be on our mind now. And we know that any integer, we're looking at an arbitrary integer. So the integer has a remainder when divided by 5, and that remainder falls somewhere on this clock. It's either 0, 1, 2, 3, 4, 5, but I'm going to call a the integer. We now know that we're given that the integer is not divisible by 5. That means that it does not fall at 0 on the clock. That means one of 4 different things must be true. It is either its remainder when divided by 5 is either 1, 2, 3, 4, 5. Whoa, there should not be a 5 there. Sorry. Okay, not a 5 there. So we have a number. Sorry, we have a number. We know by the division theorem that when it is divided by 5, then it has a remainder that is either 0, 1, 2, 3, or 4. We know in this problem that the integer is not divisible by 5, and therefore its remainder is either 1, 2, 3, or 4. So the first case is that the number, case 1, is that the number is a is equal to 4k plus 1 for some integer k. So this is that the remainder is 1. Okay, so now we want to show that the square of the integer leaves a remainder of 1 or 4 when divided by 5. So that means that we want to show that a is equal to 5j plus 1, or a is equal to 5j plus 4 for some integer j, for some integer j. Okay, so that's sorry, a squared, the square of the integer, not the integer itself, the square of the integer. So what are we going to do? We're just going to square the integer. So when we square a, we're left with Okay, sorry, I made another mistake in here, which is that we're interested in divisibility by 5, not 4. So this is not a 4, it's a 5. Sorry. So this is just using the division theorem. Sorry for all the mistakes right now. So this is left with so 25k plus 10 squared plus 10k plus 1. Okay, so you factor out a 5 and you've got 5k squared plus 2k, all right, plus 1, plus 1. All right, so we're done. We did it. We showed that a squared, here's our j. It's 5j plus 1 for some integer j. So the remainder is 1 for a squared. So we've shown in this first case that if a's remainder is 1, then a squared, its remainder is either 1 or 4. In this case, its remainder is 1. And so we've just done the first case, and you can do the other cases similarly. That's all. So that's everything. I hope this was helpful. And I'll stick around for just a couple minutes. And also, please note that James has office hours at 2 p.m. And I think that James is a fantastic TA. I just have to give a plug because I mean he's really good. So I just had to give a plug. If there are any questions though, I'm going to stick around for a couple minutes.
Thanks.
So I've got a question. I don't know if I can just
Go ahead.
When you're setting up these the induction problems, can you just choose which one instead of PN? Can I just choose it to be like PN minus 1? Can I?
You mean
Or is
like
it that I have to, or is it that I'm because I'm
like you can either choose to prove that Pn implies Pn plus 1 in the inductive step, or you can, and that's for every n greater than or equal to 1. Sorry, ignore that. You can either choose to prove that Pn implies Pn plus 1, or you can choose to prove that Pn minus 1 implies Pn. You can do either one.
Yeah. So
that's the question.
So I can just designate that Pn minus 1 and then just set up the problem. Okay.
Oh, you mean like, I'm not sure I understand your question. If you need to draw on the screen, then go ahead. Let me clear. So if you need to draw to explain it. I'm not sure I understand the question, but I think.
So like at the beginning of these problems, we always set up Pn, right? Or P, like the proposition, right? Can I have that proposition be the proposition of n minus 1 instead of the proposition of n for all? Like if that's the way, if it seems easier to do that, or I guess.
Well, not exactly. So you always want to set it up as P of n because you just want to show that P of, so in our problem, we wanted to show that a certain statement was true for every n greater than or equal to 1. And so all we're doing at the beginning when we make up these predicates is that we're just saying this is the statement when n is equal to 1. This is the statement when n is equal to 2. This is the statement when n is equal to 3. And this is this, and so on. This is a statement when n is equal to 4. And our goal is to say that each of these statements is true. So you don't need to worry about whether you're putting in n minus 1 or n in at the beginning. It doesn't make a difference. I think you might be asking because you want to prove Pn minus 1 implies Pn. Is that?
Yes, exactly. Yeah.
So n is n minus 1 is a placeholder for a number. So if we want to show that Pn minus 1 implied Pn, then that we would do it for every n greater than or equal to 2. So what you would be doing in your inductive hypothesis is showing that first P of 1 implies P of 2, and then that P of 2 implies P of 3, P of 2 implies P of 3, and so on. So you're doing it for an arbitrary value of n. So the predicate's not, you don't need to set up the predicate in terms of n minus 1.
Okay.
Yeah.
That makes sense. Okay.
Does it? I mean, I don't think I explained that very well.
Well, I'm just having trouble because I'm dealing with like the problem where I'm not like able to set it up where I'm getting A of n and B of n. Does that make sense? And then I can like equate them together. So in this, I don't have like a B of n in these induction problems, and so I'm struggling with how to relate.
Oh, you don't have a P of n.
Well, I have a P of n, but like for like the summation problems, for example, it's like you have the A of n and the B of n are two like separate. And then
You want to show the two sequences are the same.
Yeah, exactly. But in this case, I don't have two sequences. I just have like a statement is divisible by 3, like trying to prove that, and I'd do it by mathematical induction, and I'm getting stuck.
Okay, so tell me what the question is, and let's write out P of n together.
Okay, so it's just use the mathematical induction to prove that for every integer n greater than or equal to 1, 5 to the 2n minus 1 is divisible by 3.
Okay, so it's for every integer n greater than 1. We want to show that 5 to the 2n minus 1 is divisible by 3.
Yeah.
Divisible by 3. Okay, so then the way we set that up with P of n is that, so P of n is n is an integer, an arbitrary integer, and the predicate P of n is that 3 divides. So a way to say that 5 to the 2n minus 1 is divisible by 3 is to say that 3 divides 5 to the 2n minus 1. That's the predicate.
Yeah, can I just put it as 5 to the 2n minus 1 equals 3q, right? Because that's the division.
For some q, for some integer q.
Integer q, yeah. So that's what I have. And then I do the P1, that checks out. I'm struggling with the assumption part because I get, so I have Pn, I assume Pn is true. And then I'm trying to prove basically like P of n plus 1, right?
Okay, so if we want to prove P of n plus 1, then let's start, we have to start with the thing we care about, which is 5 to the 2 times n plus 1 minus 1. This is what we care about, and what we know right now is Pn. So if you're trying to show that Pn implies Pn plus 1, then we know Pn. And so we know that 5 to the 2n minus 1 is equal to 3 times q for some integer q. We need to find a way to use that.
Yeah.
So let's get this out of this. So we have 5 to the 2n plus 2. I'm just distributing here. And we have minus 1. Okay, so we're going to take out 5 squared because we want 5 to the 2n, because 5 to the 2n is here. So we take out 5 squared, and we have 5 squared times 5 to the 2n minus 1. Now, well, we want 5 to the 2n minus 1, so we're going to do a little trick, which is add and subtract a 1. So this is 5 squared times 5 to the 2n minus 1 plus 1 minus 1. So all we did was we added 0. 0 is minus 1 plus 1. Now we do a little factoring. So well, before we do the factoring, notice that this is 5 to the 2n minus 1. And Well, we know about 5 to the 2n minus 1 is divisible by 3. So therefore there exists an integer q such that 5 to the 2n minus 1 is equal to 3q. That's what Pn says. And we know that Pn is true. Then we add 1, and then we subtract 1. So now, was it that 5 to the 2n minus 1 is divisible by 3? That was the statement?
Yeah, that's the statement. Yeah.
All right. So then we're left with this. So keep distributing this and see what happens. I'll just do it. You'll have to work this out on your own, but what happens is that you have 5 squared minus 1, which is 24, and 24 is 8 times 3. And then you have this term, which is 3 times 5 squared q. And now you factor out the 3 and you're done.
Oh, okay. Okay.
Did-
Yeah, that makes
how did that go? I mean, how is that?
that is good. That helps a lot actually. So the key really is the step that I think I was missing is this step right at the very beginning of your by stating it in terms of n+1 right off the bat. I don't think I was doing
Yeah.
I was doing like the sum problems where I was adding the n term to n, right? Thinking that, right? Because n+1 would be n plus n, right?
Yeah. So wait. So you started out from the 5 to the 2n minus 1, and you were trying to say something about 5 to the 2 times n plus 1?
Well, yeah, because I was thinking if I have Pn and that's 5 2n minus 1, so Pn plus 1 would just be that, right? The P of n plus P of n, right? Because then you get P of n plus 1, right?
Oh, P of n it's a predicate. It's either true or false. It can't be added.
Okay, and I think that's my confusion is I think I'm looking at that as like a function instead of just a predicate, I guess.
It is a function. It takes integers and it produces either true or false.
Oh, okay.
And what we want to show is that this function is true for every integer n.
Okay. Yeah. Okay. Yeah, that really does help a lot. I appreciate you staying after and helping me out.
Yep, no problem. Have a good day.
Yeah, thanks, Peter.